All right, so today we're going to talk about inertia, okay, and what we call the moment of inertia. Can someone remind me what inertia in itself is? What'd you say?
Tendency for an object to keep moving or remain.
Yeah, good. An object at rest tends to stay at rest. An object in motion tends to stay at motion unless an outside force acts upon it, okay? The moment of inertia for rotational motion is the resistance to rotation, okay? And your book doesn't necessarily describe it this way, but the other physics textbook does, and I think it's a pretty good description of it, okay? So the moment of inertia is an object's resistance to rotation. Your book kind of calls this rotational inertia. It also calls it moment of inertia, which I will more often refer to it as. Okay, so the moment of inertia is recognized by a capital I, just a regular old capital I. Okay, and here's our basic equation for a moment of inertia. What would the M stand for here? Mass, and R would stand for radius. Okay, M times R squared. So our units for this inertia might be, if we take mass times radius squared, what do you think our units could be? Kilogram times meter squared. Good. Kilogram times meter squared. There's no fancy name for it. It's just kilogram times meter squared. Okay? Which means mass needs to be in kilograms and radius needs to be in meters. Okay? The equation I just gave you for moment of inertia is our most basic equation, okay? But objects that have different distributions of mass will have different equations for moment of inertia, okay? So the equation I gave you for moment of inertia are for things that are kind of like a hoop, okay? They have mass distributed around basically only the radius point that you're looking at. So that's the equation I gave you can think of as using for like a bicycle tire, okay? Most of the mass of this object is distributed at a distance from the axis point, okay? So if you think about a bicycle tire, there's a point of axes, and then there's some small kind of negligible wires or metal, whatever they're called, spokes that fan out from that axis point, but most of the mass is at a certain distance from that axis, okay, which would be the radius. So I'm going to pass out a moment of inertia table that kind of gives you some ideas of the different types of shapes that have moments of inertia and the equations that go with those shapes. We're going to go ahead and just start doing a couple problems here. We're only going to go through a few. This isn't a very long section of our notes. Let's go ahead and start doing some problems. All right, so here's what our object kind of looks like. Two masses are hanging on a bar that are 4 meters apart. So the masses themselves are 4 meters apart. First object has a mass of 5 kilograms, which is this one right here. Second has a mass of 7. The mass of the rod itself can be ignored, okay? So if it says the rod's mass can be ignored, which of our equations do you think we might be using? Okay, if the mass is only on the outside of this revolving rod, which of these should we be using? The first one. We're going to use that hoop equation. So even though it says these are on a rod, it says the mass of the rod is negligible. So the mass is distributed on the ends of this rod, which when it rotates will make a hoop kind of like shape. Does that make sense? That's why we're using that equation. All right, we're going to calculate the moment of inertia when the rod is rotated through the center axis point. So that means that this right here will be our center. What's the radius then for each of these masses?
2.
Yeah, so this is 2 meters, and this would be 2 meters. Okay? What we have to do for these, since they are not equal masses, we have to solve the moment of inertia for the first mass and the moment of inertia for the second mass, and then we'll add them together, okay, to find the whole system. So we're going to find the moment of inertia for this first object first, this 5 kilogram object. So we'll say I equals mr squared. Okay, and if you want to keep them labeled separately, you could say, you know, I of the first object, or I of the 5 kilogram object, or however you want to label it. But this is moment of inertia of this left object. Okay, so I'm just going to label it I sub 5 because it's the 5 kilogram object that we're looking at. Okay, you could label it with whatever you want. All right, so the mass of that object is 5 kilograms. Radius of the object is 2, right? Not 4, because it's not 4 meters from the axis point. It's 2 meters from the axis point. So 5 times 2 squared is going to give us 20 kilogram times meter squared. So now let's try it for the 7 kilogram mass. Nothing changes about the equation. We're just going to plug in our mass, which is 7, times our radius, which is 2. You square only the radius, and that gives us what value? 28. 28 kilograms times meters squared. Okay, so now we have the moment of inertia for each of those sides. We have to just add them together. So our total moment of inertia for our entire system is 48 kilogram times meter squared. Okay? Questions? Okay, so we're still dealing with that same system, still dealing with both of those masses, the 5 kilogram and the 7 kilogram mass, except this time the axis is rotating, or it's not rotating around the center axis point, it's rotating around the end, like we talked about. Okay, so this is kind of what it should look like. Okay, so now our axis point is right here. It's rotating now around the end rather than through the middle. Okay, at the end. So we're going to do the same thing. We're still going to use our hoop equation because as this thing rotates, it's going to have basically 2 hoops that it's going as it's rotating. Okay, it's going to have 2 hoops worth of mass. Does that make sense? Can you visualize it rotating in your head? It has 2 separate kind of hoops. So we're going to solve those and then just add them together like we did the last one. Okay? So we're going to solve for our 5 kilogram mass first. Okay? So I'm just going to label it I sub 5 again. We're still going to use our m times r squared equation because the mass is distributed basically on the ends of this radius. Okay? The radius of this 5 kilogram object is going to be what? How far is it from the axis point? It's only 0.5 meters from the axis point. So we'll take its mass times its radius and we'll square just the radius term. The radius is however far it is from the axis point. So it's how far the mass is from the axis point. So since in the last problem we chose our axis point to be the center of the rod, that's why we divided it by 2. Okay, but here, since we've chose our axis point to be at the end, we're just going to tell exactly how far each mass is from that axis point. Okay? Yeah. Okay, so what did we get for our value of our moment of inertia for the first mass? 1.25, okay, or about 1.3 kilogram times meter squared. And then when we look at our 7 kilogram object, we'll take moment of inertia of our 7 kilogram. We'll take our mass. And our radius of our 7 kilogram object is 4 meters plus 0.5 meters, which is 4.5. Does it make any difference to us about this little, if there's any leftover rod at the end? Yeah, it doesn't matter. And they told us the mass of this rod is negligible, so we don't care about the mass of the rod at all. So if there's any of that left over, it doesn't matter to us. Okay? So what do we get for our second moment of inertia here? 41.75? Okay. So all we're going to do is add these two together, which gives us a grand total of 143 kilogram times meter squared. All right, and here's what we do to, this is how we can use that, okay? We're going to take our net torque is going to be equal to our moment of inertia times alpha. What's alpha equal to? Angular acceleration. So this is an alpha, this is moment of inertia, and this is torque. Okay, so this equation is equal to Newton's second law, except this is for rigid objects in rotation around a fixed axis point. Okay, do we remember what the equation for torque is? The one main equation that we can always use for torque is FR or RF sine theta. Sorry. RF sine of theta. Okay, that's one we can always use. We could use R perpendicular times force, or R times F perpendicular, or we can use RF sine theta. Okay, what does the theta angle correspond to between what two objects? When we look at torque and we look at our theta, it's got to be between the radius and the force that's being applied. Okay, so that theta angle has to be between our radius and between our force. Okay, let's try some of these problems with our new Newton's law equation. Okay, this says Brad's bike has a radius or a wheel with a radius of 0.38 meters or 38 centimeters. It's given an angular acceleration of 2.67. We apply a force of 0.35 newtons to the edge of the wheel. What's the wheel's moment of inertia? Okay, so here's kind of what our wheel might look like. We're applying a force somewhere along this edge. It doesn't really matter where. I just happen to pick the top of 0.35 newtons. Our radius is 0.38 from our center axis to our force. So that's going to be our radius perpendicular. Or we can say that our theta angle is equal to 90, right, because it's a perpendicular. So if we want to solve for moment of inertia, there's a couple different ways we can go about this. We could solve for moment of inertia using which of our moment of inertia equations? I equals, the basic one, m times r squared. We could use that equation. Do we have all of those variables to solve for moment of inertia here? No, we don't have a mass, so that won't work. The equation we just learned says that net torque is equal to moment of inertia times angular acceleration. Do we have all of those variables? We have everything we need to at least to solve for those. Okay, we don't have torque, it wasn't given to us, but we have both a force and a radius that we can use to solve for that. Okay, so let's go ahead and do that first. Our force is equal to 0.35 newtons. Our radius is equal to 0.38 meters, which means our net torque here would be Thank you. 0.38 times 0.35 gives us 0.133. And our units for torque are? Good. Newtons meters. Newton times meters. So now we have a torque. We have an angular acceleration which was given to us in our problem. Remember, 2.67 radians per second squared. So we're going to take torque equals I times alpha. 0.133 equals moment of inertia times 2.67. Alex, what'd you get?
0.0498.
Good. 0.049, what's our units? Good.